Welcome to our talk presenting our survey paper with the title Visual Cue-Based Corrective Feedback for Motor Skill Training in Mixed Reality, a Survey. My colleague Alexander Wiebel and I, Florian Diller, are from the University of Applied Sciences in Worms, and we represent the User Experience in Visualization Research Group. This paper was written in collaboration with the University of Leipzig, in particular Gerik Scheuermann from the BSV Research Group. First, I want to give you an idea of what to expect from this presentation. In the beginning, we will have a look at the background, which involves the definition of terms and introductions of concepts, which will help us understand connections later on. Then, I will give you an overview of our methodology, what papers we chose to analyze, what our scope was, and how we acquired said papers. Then we will go ahead and have a look at the classification and insights that go along with the analysis of the selected literature. Subsequently, we will lead an exemplary discussion about papers representative and exceptional for the body of literature we analyzed. And in the end, I will give you a conclusion of what our contribution of the bigger picture was, including our main findings and open questions. In today's society, we heavily rely on seated activities in professional as well as recreational context. To retain good health, physical therapy and exercise become more important. These exercises typically involve motor skill learning, as we strive to improve our performance in the movements, which is important for health. Modern technology has over the years grown to help us with performance of these motions. In particular, mixed reality can provide powerful visual feedback to help us with correct exercise motion. When we consider visual motion feedback in mixed reality, there are numerous topics connected. Of course, visualization is at the core of what we want to analyze. Which visualization techniques are used to give feedback and what does this imply? It is also to be considered what mixed reality technologies are used and what they are able to achieve. Immersion plays an important role in motion feedback. Eiselstein, for example, established in 2004 that immersion and presence can help with motivation. This could be especially useful for exercise-related systems. Furthermore, the field of instruction is of interest. The systems used to offer instructions can make a big difference in the user experience. Feedback is a term we have to establish and clarify its meaning, as it is used in various contexts. Lastly, there can be gained further insight when we look at the specifics of skill learning in particular. Early and more recent inventions have brought up various different mixed reality technologies. As we try to select literature to analyze, we have to make a choice what technologies to consider. To do this, we follow the reality-virtuality continuum of Milgram et al. From 1994. They consider a spectrum between reality and virtuality. Every technology that involves elements of both ends of the spectrum is included in the term mixed reality. That means that both augmented reality and virtual reality are considered mixed reality. When giving feedback for tasks, instruction is inevitable. Different definitions are used for teachers, systems, professionals, or materials providing instructions. In the following, I will clarify our definition of the terms to establish a common level of understanding. When Fitz and Posner in 1967 used the term instructors in their work Human Performance, they referred to teachers and professionals giving feedback. We use this to refer to the real people still involved in the learning process. In contrast to that, Hattie and Timperley in 2007 established the term agent. This could be used for anything involved in the learning process, like teachers, peers, books, parents, the learning person themselves, or the experience. This is a term that might refer to the computer system as a teaching entity. The term feedback has a rich history and is used in various contexts. In computer sciences, for example, it is frequently used for the response of a system input. This is often a small visual or auditory cue for an interaction with peripherals, although it originally derived from electronics. Here it describes the process of feeding the output of a system back into its input. Analogically to that in education or instruction, it describes the process of giving an individual information about their performance, as seen in the figure below. This feedback loop can be enhanced by a machine, for example, a mixed reality system. In our analysis, we exclusively consider literature that uses corrective feedback. That means educational feedback which enables the user to correct their behavior. This was established, for example, by Lizakovsky and Wahlberg in 1982 and Hattie as well as Timperley in 2007. As we venture further in the topic of visual motor feedback, we see that it is firmly linked to skill learning. We have to consider that the users are trying to improve the performance at a skill. To analyze and categorize visual cues, it is important how users might progress on their performance. Fitz and Posner describe in 1967 stages of learning in their work Human Performance. They divide the learning process in 3 different stages: the cognitive, associative, and autonomous phase. When adapting a skill, one usually successively passes these stages, although the affiliation with either one could not be entirely clear since the learner transitions from one stage to another smoothly. Additionally, it is possible to revisit former stages to relearn or correct the performance. The cognitive stage, which refers to the entry point of acquiring a skill, involves the gathering of information. Detached actions are identified and learned, much progress is made, but the performance remains inconsistent. In the following associative state, the disjointed actions are put together. Here the learner performs disjointedly and small gains are made. The autonomous stage is reached after much time, effort, and practice went into the learning of the skill at hand. But when this is achieved, the execution seems unconscious and actions can be performed automatically. For example, when driving a car, we do not consider every pedal activation or interaction with the steering wheel. Our literature selection targeted approaches that involve mixed reality, as I defined before. We exclusively included literature which used corrective feedback, as it should enable the user to correct his or her performance. Additionally, we focused on literature since 2016. This year marks the market launch of the HoloLens by Microsoft. We consider this release an important milestone in the field of mixed reality, as the capabilities of this augmented reality headset provided innovative and new ways to develop visual feedback systems. To identify appropriate papers, we relied on snowballing. Using the related works of surveys with similar topic to ours as a starting point, we considered each reference and citation to find novel literature for the field. This proved to be highly effective, as we were left with 39 papers after discarding the approaches that did not match our criteria. The figure on the right shows an important work related to ours and its connections to other papers. Newman et al. Wrote an important systematic review on interactive virtual reality in sports. As a result of our classification, we assembled an exhaustive table as a reference, which you can see here on the right. The first two top rows contain the authors and a reference for each work. The first two columns show the classes and features we selected. The very right column contains the percentage of each feature occurrence to easily refer to. In the following, I will give you an overview of the different classes we analyzed. Mixed reality technologies distinguish between the technologies used in each approach to provide visual feedback. The class point of view helps us to evaluate from which perspective the user perceives the feedback. The abstraction type represents a higher level class for the type of visual cues. Temporal order gives us information of when the feedback is given in relation to the movement execution. The stages of learning give further insight on which level the surveyed literature provides feedback. We distinguish the type of publication venue to find insights on which features are important to varying target audiences. The body parts given feedback for are linked to the corresponding sports and use cases. Lastly, dependent on the use case, different visual cues to provide feedback are necessary. Now I will elaborate on the classes in detail and explain insights we get from the analysis of each feature. Optical see-through headsets provide an immersive way to offer augmented reality feedback. Representative for this is, for example, the HoloLens from Microsoft I mentioned before. Video see-through headsets are an alternative way to offer augmented reality feedback. Usually, the video feed of a VR headset will be passed through and combined with virtual feedback. Projection-based augmented reality uses projectors to bring virtual content into the real world. Cave automatic virtual environments, caves in short, involve larger rooms. VR glasses can be used without video pass-through to provide immersive visual feedback. Lastly, room-mounted displays can act as augmented mirrors and provide motion feedback in an intuitive way. When looking at the distribution of different technologies, we see that room-mounted displays are dominantly represented. This may be attributed to their relatively inexpensive and simple implementation. With optical and visual see-through plus VR headsets combined, we can see a broad representation of head-mounted displays. A first-person point of view can offer an immersive way to provide feedback. However, often the body parts provided with feedback are limited to arms. Feedback for the spine, for example, is difficult to implement. A third-person view can show the whole body and therefore present a holistic approach to motion feedback. In some approaches, we see first and third-person perspectives combined. They each offer individual advantages and disadvantages. A few systems provide visual feedback to the instructor as defined before. These are special cases and connected to the third-person point of view. The distribution shows that a third-person perspective is dominantly used throughout the literature. This can be directly linked to the large number of room-mounted displays. We will see a connection to this again. We can classify the visual cues in different abstraction types. The directional approach provides the user with feedback in which direction the movement is to be corrected. In the picture below, we can see arrows point in the correct direction. A positional feedback type shows where certain limbs or joints have to go to represent the correct motion. In the center picture, we can see the correct positions for the feet. Lastly, guidance feedback shows the position where certain joints or limbs have to be next. The right picture shows an outline which represents the correct arm position. The distribution shows us a large quantity of positional feedback among the surveyed literature, sometimes connected with directional feedback. It could be that purely directional feedback is avoided since it would be hard to estimate the distance to the correct position. With playback feedback, the user receives the feedback to his exercise after it is finished. Real-time feedback enables the participant to correct movements in real time. This has the advantage that it does not require an additional cycle for correction. Upcoming feedback shows the user what motions are to be executed next. This can sometimes lack the needed interactiveness. The distribution shows predominantly approaches with a real-time approach. In connection to the large amount of third-person perspective and root-mounted displays, we can already observe a trend of augmented mirrors among the surveyed literature. As mentioned before, the learning stages of Fitz and Posner are overlapping, so clear assignment is sometimes not possible. However, a classification in this regard can give us some insight on which level the feedback is given. The distribution shows us that the literature was predominantly categorized in the associative learning stage. This could mean that when the sub-actions are connected, the visual motion feedback might be most helpful. When considering how the learning stages are connected to the feedback types, we found that a guidance type feedback would be most suitable for a beginner in the cognitive learning stage, while graph-type visual cues are most likely more helpful to users in the autonomous learning stages. The distribution of publication venues shows us that over 80% of the literature was published in a computer science venue. Most of the approaches in the VR, AR, and MR sector, and another big part in the field of human-computer interface. Some approaches were published in the field of medicine, health, and sports. It is to be mentioned that these approaches often had a different focus to the ones in computer science, as they tend to focus more on the effects on the body and treatment of individuals. Besides few research attempts focusing on the feedback for arms and legs, most feedback was provided for the whole body. This can be directly connected to the large examples of third-person augmented mirrors, as there are numerous examples which provide both a feedback for the whole body and a third-person view. In large part, the use cases we identified were individual sports. This could be attributed to the fact that head-mounted displays are usually suited for the individual. Furthermore, feedback is mostly given to the individual, even in team sports.
So far, we have given a high-level overview of all features we used in the classification of the surveyed literature. My part of the talk will focus on the classification feature which is at the core of the paper and which thus also occurs in the title of the paper, that is, the visual cues. Examining the considered literature, we identified 13 different types of visual cues. I will go through all of them to describe them, to provide examples, and to mention certain characteristics of each of them. The first very simple cue we considered is text. Here, information is provided through letters, words, and simple symbols. The example shown on this slide lists names of body parts together with symbols indicating if the position and orientation of the mentioned body parts fit those of the target pose. Another way of giving textual cues are numbers showing angular or positional differences or, as shown in the photos on the right, textual explanations of what the user should do. Although textual cues are not visualizations in a strict sense, we consider them to be visual cues when contrasting them to auditory cues or other cues not perceived with the eyes. Color coding, the second considered cue, highlights areas of the body or the whole body pose by colors indicating if the pose taken by the user is correct or how correct it is. The image on the left shows an example, an outline of the body or of certain parts of it can provide feedback without causing significant or any occlusion at all. It is usually used together with a video stream or an avatar showing the actual pose. Due to the limited occlusion caused by the outline, the actual pose remains visible even when the target pose is shown. The two leftmost images show an outline together with a live video. The right image illustrates how outlines can be combined with avatars. Here the avatar is a virtual shadow of the user and the outline is used to provide feedback for golf strikes. The next visual cue we considered is highlighting the intended end position of a movement. The left image shows an example where a climber should reach for climbing holds, which are highlighted. This means the climbing holds are the intended end position of the climber's arm movement. In this case, the end position is located at the position of a real-world object, here the climbing hold. In other cases, like physiotherapy exercises, the position can be on the floor or in mid-air. While only the intended location of certain body parts is shown by the end position cue, avatars are often used to show the complete pose a user should take. Avatars come in two main types. Here we see transparent avatars showing the target pose on top of the currently taken pose. A transparent target avatar can be used in combination with a video or a 3D or 2D opaque avatar showing the current pose to create a sense for how movements should be executed. The transparency of the target pose or target movement prevents this visual feedback from occluding the actual pose. The second main type of avatars is opaque. In 3D, an opaque target avatar depicting the target movement can be superimposed with an avatar showing the actual movement. If the two objects overlap, they create an intersection effect, as can be seen in the left image. In the right image, one can see how the opaque mannequin-like avatar occludes large parts of the skeleton-like pose representation. Additionally, the right image shows that choosing visually distinct types of avatars can support users in distinguishing the different avatars and their purpose. In this case, the skeleton shows the target pose. The correction cues for some movements may be hard to perceive. This can be the case if the body part to be corrected is out of sight for the user, or the correction and movement is minimal. In such cases, movements might be easier to comprehend if they are represented by an abstraction of the movement rather than showing the actual movement or start and end position. In the left image, the abstraction is still shown in 3D space. The right image, not actually being in mixed reality anymore, goes even further and shows an abstraction of the pose in 2 dimensions. If a video stream is implemented in the system, it can be used with other cues like avatars to provide feedback. The video can either show the actual pose as context to the other cues, or can show the target pose with the other cue as the context. This way, the system can depict what movements to execute next, a sequence of movements, or correction cues. Video overlay is mostly used in augmented reality approaches and benefits from 3D implementation, but it is not limited to 3D. The next cue shows the difference between the actual and the target pose by connecting them with a line or an arrow. This connection is called rubber band because it extends or shrinks depending on the difference between the two poses. For the visualization, 3 parts are shown. These are the actual pose, the target pose, and the rubber band. This and the following cue are strongly related. In contrast to the rubber bands, for the arrow cue, only 2 parts are visualized: the actual pose and the arrows or similar objects showing the direction of the intended movement. Each arrow is similar to a rubber band in the sense that it points from a joint or limb of the actual pose towards a joint or limb of the target pose. While the rubber bands connect the poses and thus have a predefined length, the arrows can be shorter or longer if their purpose is only to indicate the direction of the suggested movement. Furthermore, the arrows have heads indicating their orientation, while the rubber bands do not have a specific orientation. Movements can be described by lines that represent the path of a certain joint or bone in space over time. These so-called trajectories can show the user where or along which path to move next or how to correct the movement executed. In the left image, Clark and others combine trajectories with a video overlay in their approach. The right image shows more abstract 2D trajectories in a live system. Most of the presented cues represent the feedback information in the same space as the body movements. The feedback we summarize under the term graphs is different. Here the data obtained by tracking the motion of a body is plotted as curves in 2 dimensions. This classical visualization of numerical data provides a detailed but abstract way to present movement information and correction cues to the user or instructor. In the surveyed literature, it is rarely used. The last cue that we found in the surveyed papers is strongly connected to the overall structures of human bodies, that is, to the skeleton with its bones and joints forming the limbs. Because movements of the skeleton are determined by rotations of the bones around joints, feedback can be given showing the angles certain limbs should turn. These angles are commonly illustrated using circular arcs or segments of circles. Usually, the visualized angles are relative to the closest joint. Arrows and other difference visualizations usually illustrate the absolute difference between actual and target pose. This concludes the detailed description of the 13 types of cues we identified. From our overview table, one can see that a large portion of the surveyed literature uses multiple cues together. In the table, we classified only those papers as using a certain cue, in which the cue plays a central role for the specific approach presented in the paper. Video and some kind of geometrical representation of the pose is present in most approaches to provide context for the feedback. Video and some kind of geometrical representation of the pose are also dominant when only considering those approaches where they play a central role. Angles, rubber bands, and arrows showing a certain direction are used much less frequently. This difference becomes even more obvious when plotting the percentage of papers using a certain visual cue, as can be seen on this slide.
In the following, we will discuss examples that are widely spread among the surveyed research attempts, as well as unique ones. This will give you an understanding of how the body of literature was composed. Starting with the representative examples, I want to highlight the work of Oka and Makino of 2021, a real-time feedback system of strength training with motion capture and head-mounted display. They utilize an abstract skeleton to visualize real-time feedback. This is seen often throughout literature, for example in Furukawa et al. From 2019 or Escalona et al. From 2020. VR glasses are a common way to provide feedback, as we discussed earlier. Ikeda et al. Use VR glasses as well in their work, AR-based self-sports learning system using decade dynamic time warping algorithm from 2018. The third-person perspective enables the viewer to receive corrective feedback for the whole body, a variant which is quite common in the literature. The option to choose between playback and real-time feedback enables the user to take advantage of 2 temporal order types. The appliance of a third-person feedback in VR can be seen in several other approaches, for example Hoang et al. From 2016 or Ware et al. From 2020. The approach of Barioni et al. Ballet VR, a virtual reality system for ballet arm positions training, from 2016 shows the use of a room-mounted display to provide feedback. VR glasses are an option mentioned in the paper as well. A transparent target avatar on top of an opaque actual avatar shows upcoming poses for the users to imitate, as seen in the picture. Similar approaches can be observed in the works of Han et al. From 2016 and Cao et al. From 2020. As the last representative example, we will have a look at the research attempt from Oshita et al., Self-Training System for Tennis Shots with Motion Feature Assessment and Visualization, from 2018. They provide a great variety of visual clues, including an opaque avatar, textural feedback, limb angles, and arrows, some of which can be seen in the figure on the right. Their approach to showing feedback utilizing an opaque avatar is seen analogically in the work of Huang et al. In 2016 and Ikeda et al. From the year 2018. Opposing the representatives, we want to point out exceptional works which are a singularity within the literature body. The work of De Barber et al., Augmented Reality Visualization of Joint Movements for Physical Examination and Rehabilitation, from the year 2018, utilizes an AR headset to show instructors feedback. Realistically rendered bones are combined with limb angles to enhance physiotherapy, as seen in the picture. This setting and target group is unique in the literature we surveyed. Shiro et al. Offer another exciting and unique approach to provide feedback in their work, Interposer, Visualizing Interpolated Movements for Bouldering Training, from 2019. As seen in the figure, images are synthesized in a manner so the beginner can interpolate the executed movement successively matching the expert movement. This is achieved utilizing generative adversarial networks, a machine learning technique. Vidal et al. Present us an interesting work in Body Lights, Open-Ended Augmented Feedback to Support Training Towards the Correct Exercise Execution, from 2020. Lights attached to the body visualize the movement of the trunk. The user has to match the projected lights to the crosshair, which is located in the room. This abstract feedback approach is unique in the surveyed literature. As the last exceptional research approach, I want to highlight the work of Kosmala et al. From 2017. ClimbVis, investigating in situ visualization for understanding climbing movements by demonstration. Utilizing a projection-based approach as well, and positions, or alternatively, an instructor is projected on a wall as seen in the figure. The room size application, as well as the instructor showing upcoming movements, make this research attempt unique. In the following, I want to give you an overview of what conclusions we drew from the analysis of literature classification. As I stated before, we identified various approaches that involved augmented or virtual mirrors. These approaches included a third-person perspective and whole-body feedback. Additionally, we observed that positional feedback is dominant, though it is sometimes combined with directional feedback. This hints at the utility of certain visual cue clauses. Furthermore, the classification we applied to the literature concerning Fitz and Posner's learning phases enables a better feedback design in regard to target groups. The high occurrence of the associative skill learning phase gives insight into the visual cues in literature, as well as inspiration for new and innovative types of feedback. Lastly, we identified a variety of visual cues. This not only helps to choose the according feedback for a given system, but could also help to develop further visual cues for specific needs. With the work at hand, we analyzed the state-of-the-art literature. To find causalities among the features we observed, a deeper analysis would be necessary. I will go into detail on what open questions we see later on. The scope of this paper did not allow for an in-depth analysis from a cognitive, therapeutic, or user experience standpoint. Many research attempts focus on tool handling. The visual cues and techniques used in tool handling were not the subject of this paper. Lastly, we cannot provide clear indication of where the learning stages of Fitz and Posner apply. That means that the insights from this category are limited and merely a hint for future research. The considerations for the surveyed literature left us with several open questions that require further assessment. First, the connection between visual cues and learning phases is yet unclear. We found hints on what could be beneficial, but an additional analysis of the connection between these two concepts could be valuable for future feedback design. Furthermore, we identified mainly approaches providing feedback for individuals. Additionally, analysis of the visual feedback for the interaction between humans could be interesting for the research community. In various sectors, performance consists of a large degree of interaction between humans. For example, team sports like football and soccer or dancing could profit from. We intentionally excluded research attempts that provided feedback for tool handling, as this exceeded the scope of this work. Yet it could be beneficial to consider the visual cues and techniques used in this sector. Although we gathered a large variety of visual cues and discovered several hints on the utility of them, it is yet to be uncovered what the nature of the visual cues holds. Feedback design could substantially benefit from an in-depth understanding of these visual cues and the connection to existing concepts. Thank you for your attention. If you have more questions, I would be happy to hear from you.